Okay, so today we're going to wrap up Chapter 9 on rational expressions today by solving rational expressions. Here's the plan. So we'll be solving rational expressions both algebraically and graphically. Today we'll before I get to that, of course, we'll really need to have a good, strong understanding of algebra and factoring today. So in other words, you really have to understand how to do the sum product rule, for instance, or difference of squares can come around. I don't know if we'll do an example like that today, but make sure you have a good understanding of algebra and factoring. We'll also compare the solutions we get from solving algebraically to the solutions we get from solving graphically. You'll kind of be disappointed by that. It's not really all that exciting, but we're going to whip through this as fast as we can because I think a lot of this is stuff we've covered before. But here we go. One last thing though, we have a quiz on Chapter 9 next class that covers everything that we've learned about rational expressions. There shouldn't be any big surprises to it. Here we go. All right, so before we start, let's just do a little quick recap. Suppose we have the following rational function. Identify the x-intercepts, the vertical asymptotes, and the points of discontinuity. I would appreciate if you just pause the video here and give this one a try on your own, and then I'll go over it in a second. Okay, so hopefully you were able to go over this one. Basically, to solve for this, we have to factor everything first, right? So the x-intercepts, hopefully you remember, are just the zeros that show up on the top. Vertical asymptotes are the zeros that only show up on the bottom, and then points of discontinuity are the ones that show up on the top and the bottom. So let's factor this first. We're going to say f of x is going to equal, on the top here, we just have a normal sum product rule question. So we're looking for two numbers with a sum of -3 and a product of -70. Well, the two numbers that come to mind for me are -10 and +7. So we'll say that's x minus 10 and x plus 7. Now we're going to put this all over whatever this is going to factor down to. Now this is an adapted sum product rule question, so this one's going to take a little bit more work. Basically, we're looking for two numbers that have a sum of 15 and a product of 2 times 7, so a product of 14. So you got to ask yourself, what two numbers would multiply together to be 14, but would add together to be 15? Well, those two numbers would be 14 and 1. So what we can do is we can split apart this middle term using 14 and 1. So 2x squared plus 15x plus 7 becomes 2x squared plus 14x plus 1x plus 7. So that's where the 14 and the 1 went. Then the next step is we put brackets around the first two, brackets around the second two, and then we just start factoring. So this piece here, we can factor out a 2x. So this is going to be 2x times x plus 7, plus on this piece, there's nothing we can factor out. So when there's nothing, you just factor out a 1. So plus 1 times x plus 7. Our hint that we've done this correctly is that there's the same factor on both sides here, x plus 7 and x plus 7. So I can write this as x plus 7 times 2x plus 1. Okay, so that's factored now. Let's move this back over here. So x plus 7 times 2x plus 1. Now that it's in totally factored form, we can find all that information it was asking. So our x-intercepts are the zeros that only show up on the numerator. Well, notice x plus 7 shows up on the numerator and the denominator, so it's not going to be that one. But the only one that shows up just on the numerator is x minus 10. So our x-intercept would be x equals positive 10, because it's whatever makes this equal to 0. Our vertical asymptote, so VA, is just whatever shows up only on the bottom. Again, x plus 7 shows up on the top and the bottom, so we have to just look at 2x plus 1. Set that equal to 0, you're going to find that x is going to equal -1/2, or -0.5, of course. Then for our point of discontinuity, or pod, as I often call it, pods are whatever show up on both the top and the bottom, the numerator and the denominator. So that's x plus 7. That means our point of discontinuity is going to be x equals -7. And those are always tricky, because if you were to graph this, like in your calculator, it wouldn't even show up. Like it would just look like a continuous line at x equals -7. But the reality is it's not continuous at that point. It just gets infinitely close, both from the left and from the right. Anyway, that would be the answer to this one. Really, this whole chapter is basically, can you factor an equation, right? Like that's about how hard this is going to get here. If you're not good at factoring, of course, this unit is going to give you a lot of trouble. But aside from that, if you do have a good background on that, it's not too much. It's just thinking about where your x-intercepts, vertical asymptotes, and pods are. Anyway, moving on. So today we're going to be talking about solving rational expressions. So we'd like to figure out the value or values of x that make a rational expression true. So in other words, when you have like a rational expression on one side of an equation and a rational expression, or any other expression, like in this case, on the other side. So the denominator is what's going to give us trouble here, especially when there's an x down there, right? Solving for an x when it's down in the denominator is just tough. Bottom line is what I usually do, like I'm going to simplify this as much as possible. I'd say just acknowledge your NPVs, but then multiply away your denominators. There's another trick that we'll get into on a question a little later on this that works for very specific questions, but we'll worry about that when we get there. First things first, acknowledge your NPVs. So before I even start this question, I'm going to say my NPVs are x cannot equal -6. Okay, so in other words, if we find -6 as an answer to this expression, it doesn't actually work because it's an NPV. You'd be dividing by 0. Next step, of course, multiply away your denominator. So it's times by x plus 6 on both sides. The left side's easy. If you times by x plus 6, you're just left with 16. The right side, however, is tougher. It's going to be 4 minus x times x plus 6. So you got a little bit of like, you know, the FOIL process to actually get this to work. Let's do that though. So 16 equals 4 times x is 4x. 4 times 6 is 24. Negative x times x is negative x squared. And then negative x times positive 6 is minus 6x. Then I gather together all your like terms. So we got 16 equals, well, 4x minus 6x is negative 2x plus 24 minus x squared. And this looks like an absolute nightmare, right? So this is all jumbled around and jambled. Let's bring everything to one side. And ideally, we like having a positive x squared on one side. So you know what I'll do? I'll add x squared to both sides. I'll add 2x, and then I'll minus 24. What that's going to give us is it's going to give us x squared plus 2x, and then 16 minus 24 is minus 8, and that equals 0. Now this is just a standard old quadratic. We can now solve for what x would be just by using our sum product rule, right? So we're looking for two numbers with a sum of 2, but a product of -8. And I'm pretty sure those two numbers would be 4 and -2. So we have x plus 4 times x minus 2 equals 0. And then that gives us answers where this is 0 or this is 0. So x equals -4. And the other one is where x equals +2. That's all there is to it. You don't necessarily have to verify this, especially since we've seen our NPVs. You can try verifying it if you want to, but it'll work. So yeah, so in other words, just don't worry about it too much. Or at least I think it'll work. Maybe we should verify these. Not even gonna lie. You know why? I'm thinking about this -4 here. This -4 is kind of making me go, I wonder what's gonna go on here. 6 divided by -4 plus 6 is 16 divided by 2. 16 divided by 2 is 8. Okay, so then 4 minus -4. Okay, yeah, we're good. I was double checking right there. That's all I was doing. These are both fine. I can see clearly x equals 2 would work no problem, but we're good. Anyway, moving on. All right, so another way of doing this is graphically, of course, so just using your graphing calculator to help you. You probably have a pretty good idea how to do this, but just in case you don't, that's okay, because we really don't use our graphing calculator for this kind of thing a huge amount. We seem to put the emphasis on algebraic. There's two different ways you could do this. You could do a system of two different functions. In other words, you could plug that first one into y1, so y1 could equal 16 over x plus 6, and then you could plug the second one into y2, so in other words, 4 minus x would be y2. When you do this, hold on, I've just got like a graph of it right here. I'll just try to like sketch it. When you do this, what you're going to see in your calculator, if you just have a standard set window, like so, you're going to see your graphs are going to look something like this. It's going to be like this little bend right here, and then like another bend like down here, kind of thing going on. That would, of course, just be your y1. And then your y2 is going to look something like this, right? So what I'm trying to ask is like, what on earth, when you graph both of these in your calculator, what on earth are you looking for? Well, since you're looking for where y1 is equal to y2, you're looking for where they're meeting, right? So you're looking for the intersections, or just the intersects. There you go. And the calculator keystrokes to do this, of course, are second, then press trace, and then go down to where it says 5, and then just follow the instructions it gives you. Now, another method is just to use a single function. And not going to lie, I actually usually prefer this method. I just think it's easier for me. But again, whatever floats your boat. Using a single function basically just means get everything to one side. So I would -4 and I would add x. So I would put in y1 16 over x plus 6 minus 4 plus x. Not part of the fraction, of course. Now, when you graph that, what you're going to see, and I'll just do a real quick sketch on this one. What you see if you graph that is you get something that looks something like this. It's going to be like, I don't know, it's not perfect, but hopefully you get the idea. It's going to be something like that. It kind of almost looks like a quadratic thing going on. It's just a little bit bent one way. Yeah, it's just weird. When you solve this way, what you're really looking for is where this is equal to 0. Because to solve this, you're just finding your x-intercepts. So right there, you're looking for your x-intercepts. And to do that, we just press second, and then trace, and then 2, okay? And then, of course, just follow the instructions. I think there's like a left bound and a right bound or something like that. But anyway, yeah, graphically, it's the same thing. It should give you the exact same answers one way or another. As a matter of fact, let me just go back to check the answers. It was -4 and +2. Yeah, and again, my picture here kind of sucked, but it's something like that, right? And this one especially really sucked. It was actually more like this line is like, kind of like that, -4, +2. Anyway, you get the idea. Moving on. All right, next example. Solve 3 over 2x minus 2x over x plus 1 equals -2 graphically. Express your answer to the nearest hundredth if necessary, then verify your solution algebraically. That got me excited there for a second. I was like, oh, we just have to do this graphically. So again, whatever floats your boat, whether you want to do like the single method or the two-function method. Two-function, of course, where you do this whole thing in y1. So like this whole thing is y1 and this thing is y2. And then you just solve for the intercept, or you can just bring it all on one side and find the x-intercept. Again, it doesn't matter. Whatever floats your boat. Either way, though, the solution to this, I'll save you the trouble. You can do this if you want. But the solution to this, you should be getting x equals -0.43. So that would be the solution found graphically. Now they want us to do this algebraically. It's kind of backwards how they do this. Usually they say do it algebraically and then verify it graphically. But whatever, you know what? Whatever. To verify the solution algebraically, first things first, we should list our NPVs. So our NPVs in this case, just judging by whatever we're dividing by 0 here, our NPVs are x cannot equal 0 and x cannot equal -1. Just get those out of the way first things first. Next thing, get rid of all your denominators, right? So in other words, multiply them all away. I'm going to multiply everything here by 2x first. So that's going to give me 3 minus, I got to multiply this by 2x, so that'll be 4x squared over x plus 1 equals, and I got to multiply this by 2x as well, so equals -4x. Then we still have a denominator. We got that x plus 1, so let's times by that on all of these, right? So 3 times x plus 1 is 3x plus 3 minus 4x squared equals -4x times x plus 1 is going to be -4x squared minus 4x. Yeah, there you go. Just double checking. Now we got to bring everything to one side. Something really, really nice happens on this one. It's kind of a break for us. Usually I say, oh, get all your x squareds to one side, make sure they're positive. So maybe we could just like add 4x squared to both sides. Notice if you added 4x squareds to both sides, you'd actually cancel both of these out. So these just go out the window, so we don't have x squareds anymore. That actually makes it way easier for us. Then I'll just add 4x to both sides, so that's going to give me 7x plus 3 equals 0. And then, of course, this is just a linear equation. You can just solve this just by rearranging and solving for x. So 7x equals -3. Divide by 7 on both sides, and you are going to find to the nearest hundredth x equals -0.43. So there you go. We just verified it algebraically, as backwards as it is. We could have just done algebraically in the first place. But there you go, right? So it gives you the same answer one way or another. Just in terms of accuracy here, generally speaking, algebraically is probably the better way of going. Graphically might miss a few details. Don't guarantee me or quote me on that or whatever. Like I'm just making an assumption on that one. But I would put a little bit more trust in an algebraic process. But there's nothing wrong with verifying graphically as well. All right, moving on. Next one. Oh, this is one I was alluding to earlier today. Solve x over x minus 1 equals -2x equals x plus 1 over 2x minus 2 algebraically and graphically, and then compare the solutions. So we're going to worry about algebraically first before we even do anything at all. Just acknowledge your NPVs. I'll just do it way over here so they're out of the way. Our NPVs in this case are just wherever our denominators would equal 0. So clearly x cannot equal 1 on that first one. And then if you look at the second one, it's also the exact same thing. X can also not equal 1 on this one. So they have the same NPVs. We're good to go. Now, usually, just giving you a heads up here, usually what we would do is we would multiply all our denominators away. And I'll tell you right now, that is a totally valid strategy. You can definitely do that in this question. But just notice that both of these denominators here, they're binomials. So we'd have a little bit more work to do. We'd have to like multiply everything by x minus 1. So then you have like a double dip thing going on up here. And then you have to multiply everything by 2x minus 2. And you have this big jumbled mess right here. But long story short, it would be a lot of work. Okay. Sometimes you just have to suck it up. Sometimes you have to say, yeah, there's just a lot of work. You just have to do that. But in this case, we can actually be pretty clever with this. Notice 2x minus 2 is just a multiple of x minus 1. Like if I times x minus 1 by 2, you're going to get 2x minus 2. So they'll match. They'll have matching denominators there. Well, since this is part of a fraction, if I just times the top and the bottom by 2, I'm not changing what this is equal. I'm just changing how it looks. So if I do that, I'll have 2x over 2x minus 2 minus 2x equals x plus 1 over 2x minus 2. Now notice the only thing that doesn't have 2x minus 2 as its denominator is this guy right here. But if we just times this piece, this negative 2x by 2x minus 2 over 2x minus 2, we can force it to have the same denominator as everything else. What that's going to look like is it's going to be 2x over 2x minus 2 minus, and then we times this by 2x minus 2. So it'll be, you know what, I'll just be safe here. I'll just go 2x times 2x minus 2 over 2x minus 2, and that equals x plus 1 over 2x minus 2. Okay, you might be wondering, why on earth did you do this? Well, back in Math 20-1, we actually solved equations this way more commonly than not. This way was just to say, make sure that all of your denominators are the same, and then you can just ignore your denominators altogether and just solve whatever was on the top, right? That is how we did things back in Math 20-1, because the rational expressions we were given were simple enough that we were able to do that, right? It's kind of like the log thing, where we said, oh, if you have like the log of something on both sides, if they have the same basic, just ignore the logs, right? So it works the same way. Anyway, we'll do that. Let's just ignore the denominators here. We've already acknowledged our NPV, so that's important. You'll find that you have 2x minus, I guess I'll double dip this through, but I'll keep the brackets, minus 4x squared minus 4x. And remember, those brackets are important because this has got to go inside that first before we apply the minus. And that equals x plus 1. Applying that minus through here now, we got 2x minus 4x squared plus 4x equals x plus 1. Now bring everything to one side, and again, I like having a positive x squared, so I'll bring that to the other side here. We're going to have 0 equals 4x squared. These two combine to be 6x, but then we'd have to minus it over, so minus 5x, and then I guess just plus 1. All right. So now we're looking at an adapted sum product rule question, which I know is annoying, but you know what, whatever, just deal with it. We're looking for two numbers with a sum of -5 and a product of 4 times 1, so a product of 4. So you can write that sum, -5, product, +4. Well, the two numbers that are going to do this are going to be -4 and -1. So let's break this down now. It's going to be 0 equals 4x squared. Remember, the two numbers that make this work are going to be -4 and -1. So -4x, -1x, plus 1, and then put brackets around the first two and brackets around the second two. But be careful. Remember the little rule, when we have a minus in here, when you put brackets around these second two, you got to change the sign of this middle piece, okay? Because otherwise that's going to bounce through and cause havoc, right? We don't want that. All right, now factor out whatever you can from this. So 0 equals, we can factor out a 4x, so 4x, x minus 1. Minus, out of these guys, we can only factor out a 1, so 1, x minus 1. Since those match now, we're good. So 0 equals x minus 1 times 4x minus 1. And then we just solve for where both of these pieces equal 0. So in other words, x would have to equal 1, right, for that one. And on this one, it'd have to be x equals, I guess, add 1 minus, or divide by 4. So x equals 0.25, or 1/4, or whatever floats your boat. Oh, wait, you might have just noticed something here. These are our solutions. But what was our NPVs again? Right? Our NPVs are what controls what works and what doesn't. Notice NPV says x cannot equal 1. What the heck? What's going on down here? It says x equals 1. That is a false positive. We don't actually have that. That is not a real solution. So I'm just going to cross that out altogether. Acknowledge that you found it, but cross it out because it doesn't work. So our only solution here is x equals 0.25. Then it says solve graphically. So after all that work, all that algebraic, we just have to now plug this in our calculator. Hopefully you guys know how to do it. Again, you can do this is y1 and this is y2. Whatever floats your boat. I'm going to save you the trouble here. You can try it on your own if you wish. Graphically, you're going to find, big surprise, x equals 0.25. As a matter of fact, the x equals 1 doesn't show up as a possible solution on that one. So it's like there's no secret on graphical. There was no false positives there. They had the same solution. Now it says compare the solutions. I honestly don't know what I was meaning by that. I guess we could say they're the same, right? They're the exact same solution. It's good to go. But again, it is an objective in this course to be able to solve algebraically, so make sure you know how to do that as well. Anyway, we're done. That was a relatively quicker lesson today. Page 465, questions 1, 3, 4, 7, 10 to 13. Give those a shot. If there's any in there that you're like, oh, that's too easy, or I already know how to do that, just skip them all together. Be sure that you have some good practice with factoring. quadratics, of course, especially the adapted sum product rule ones, like we've done a couple of them today. Those ones always seem to cause trouble for some people. So just make sure you've got that skill mastered, because that is going to be very, very important going on. And we're officially done chapter 9. That's it. That was all there was in rational expressions. It was like the shortest chapter ever. We only have 2 chapters left. There's one on function operations that we're going to cover the remainder of this week. And then there's another one that's on permutations and combinations. It's basically as close to a stats unit as we get without actually being a stats unit. Anyway, I'm going to stop talking now. If you need any help, you know how to reach me. Best of luck.